Why I'm not visible? Oh. Okay, fine. So today's class in the chapter Electrostatics, we are going to discuss the Gauss law and its application. So we are going to begin with the very basic of the Gauss law here. Yeah? So what all I'm going to discuss the Gauss law. The application of this is what the next chapter, what you can see the capacitor. So today, what all in this week you are going to learn, no? The conclusion of this is what we are going to use in the capacitor chapter. And if you learn the capacitor chapter, it will be very easy for you again in the current density RC circuits. All these are interrelated. So we are going to introduce the first time in the electrostatics, the conductors. If a conductor is brought into a charged system, how the behavior will be. That is what we are going to analyze in this particular with the help of the Gauss law. Okay, let me begin like this. And so already I think we had a discussion in the, if you can remember in the gravitation chapter, we had a nice discussion on the Gauss law. So let me start with this. So the flux is equal to integral of E bar dot ds bar equal to Q in by epsilon naught. Okay, this is about, so what is this quantity? So all one by one will list out. So this is called like a electric flux. This is the electrostatic field. What is ds? Elemental surface. Q in is net charge enclosed by a Gaussian surface. Okay, these are all the various quantities which we have defined here, that one. Now, first we'll talk about the electric flux. What is the necessity of electric flux? Why we have to, why I'm introducing especially that electric flux here? What is the necessity of that? So let's do one thing. Let's take a point charge. And the lines of force I can assume any number of lines of force as we know earlier. Okay, these are the lines of force due to a positive point charge. Okay, fine. Okay, now what we do is like uh, some student will assume how many, some say like a how much I assumed here 3, 3, 12, 12, 16 lines of force. Another student will assume 20, another student will assume 100. Like that, there is no some sort of like a uniformity, no, in number of lines of force. There's nothing called like any uniformity. So to bring that uniformity is what happened. We are bringing the flux idea. So what I do is like a, let me bring a surface here. I'll keep a surface. Let me draw a surface. Okay, I'll keep a surface here. So some any arbitrary shape, and the same surface I'll move it here. So what is this? This is the surface. Okay, what about the lines of force here? There are two lines of force are passing. What about how many lines of force here? Here, how many lines of force? Only one lines of force. So now, I'm going to express that the electric field to area will become flux. So now I'll come out of the idea of lines of force. If another student for same positive point charge, he may assume 100 lines of force, then he may get a different idea. So to overcome that number of lines of force, I'm bringing a concept of electric field strength. What is electric field strength? For a point charge plus Q, either you assume 100 lines of force or 10 lines of force. What is the electric field at a distance R? Will remain same. So lines of force are imaginary one. So to make that uniformity in the number of lines of force, so we are bringing the concept of the electric flux here. Now I'll calculate the field strength E bar, whether you assume 100 lines of force or 10 lines of force. What is the field strength here? Will be same. So how much field strength at the location of the first surface? It will be roughly the direction. Let me take some other color. Yeah. So how much E bar? Somewhere in this direction. So what is the value of E bar here? E2. What is the value of here? E bar is E1. What is the surface area? Let it be S. Then can you say anything about the electric field strength? Electric field strength at 2, at 1, it will be greater than 2. And look at the number of lines of force. More number of lines of force are passing at through the surface at 1 than at 2. Then instead of saying number of lines of force, I just say that flux at 1 is more than flux at 2. For that, what happen? E1, E2 is a uniform. Because what is the formula for E1? E1, what happen? We'll be using formula KQ by R1 square. What about T2? KQ2 by R2 square. R1 less than R2. So therefore, E1 greater than E2. So there's no problem with the electric field strength, because we know from the Coulomb's law what is electric field due to point charge. Okay, now I'll define, rather than say like how many lines of force, I just say what is electric flux here. What is electric flux? E1 into S. What about electric flux here? E2 into S, that one. Like this, we define it. Now, again, the where electric field strength is more at this point. So now we'll define the flux. Flux at 1 equal to E1 bar dot S bar. Flux at 2 equal to the same surface, no? E2 bar dot S bar. S is the area vector. S bar is an area vector. Now, so what we can say now, definitely from this, flux at 1 more than 2. And we know number of lines of force. To surface at 1 is in fact greater than number of lines of force of the surface at 2. Tell me like which one? I think this is the more best method, no? To express the number of lines of force. So what is the flux? Flux will give us the information regarding number of lines of force. I say flux at 1 is more, means more lines of force are passing through. How many lines? It will not tell. The electric flux will just give information of number of lines of force, proportional to number of lines of force, not how many lines of force. Are you getting the idea now? Since earlier, what happened? We didn't add a flux. No, we were concentrating more on lines of force. Now, here afterwards, we'll discuss everything about electric flux. And electric flux doesn't bother about like how many lines of force you are going to assume. It just depends upon E bar and S. So the idea of that lines of force, what happened? We are idea of how many lines of force I should assume is what we are coming out of that method. We need not to bother about that one. We need not to bother about the how many lines of force I should draw it. To make that uniform thinking, we have a idea of this electric flux here. Getting the idea now? So these are the things what happen, which because there is no any uniform in number of lines of force. To make that uniform thinking in lines of force, the idea of flux is brought here. So what is electric flux? Electric flux, what can be unit for this? What is the unit for electric field? Volt per meter. So volt meter, we can write it. What is the electric field? Electric field will be volt per meter, and this is a meter square. So unit will become volt per meter. Okay, let's go for further one. So what is the electric flux? So we'll just focus on that one. Let me take in elemental surface. Also, let me take a strip, length L, B bar. Volt meter is there, no, per meter. And I'll do one thing. Yeah. There's a uniform field is there. So this one. So now again, so I considered a now four situations. So where this will make an angle, select it be theta. So that I'll call alpha. What is the flux in the first case? What is S bar? We should define S bar. S bar is an area vector where it is, I'm going to define it as S bar is equal to area into n cap. What is the area of cross section of this strip? L into B. What is n cap? Unit vector directed normal to the area vector. So since it's an open surface, so I'm going to choose one particular direction. Let it be upward, n cap that is. Then what is the angle between E bar and n cap? It is 0. So let me take the dot product. So the flux is equal to, I need some space here. Yeah, we'll conclude here only. So the flux is equal to E bar dot S bar. So what is E? S cos 0 degrees, angle between them, E into LB. So I say flux is positive. What does it mean? The lines of force, the electric field vector is in the direction of n cap. That's the meaning of that one. Okay, let's come for this one. What is the angle between E bar and n cap? 180 degrees. So in the second case, what is the flux will be? ES cos of 180 degree minus ES, or will be minus ELB. Now, what do you mean by flux negative? The electric field vector there will be directed opposite to the n cap. The electric field vector will be directed opposite to n cap. So that's the interpretation of the flux negative. Second case, so what is the angle between n cap and E? It is alpha. ES cos alpha. So ELB cos alpha. Now, second case, fourth case, ES cos 90 degrees. So this will be 0. What do you mean by flux 0? means the lines of force are not passing through the surface. And now this, which flux will be more, phi1 or phi2? Definitely say phi1. Because here E bar is at an angle. So definitely what the amount of number of lines of force passing through that will decrease here. So flux will be decreasing, what we say. Like this for an open surface. So now you can ask questions. Why can't n cap be downward? As if you define n cap downward for all four situations, you have to make n cap downward. For open surface, you can assume n cap upward or downward. Here, let me assume it n cap upward here. Okay, agree this. So like this, what happened? We introduced an idea of electric flux. Now, when you can directly multiply the field strength into area, if field is uniform, if at all points on a surface, if electric field strength is constant, then what we do, directly we'll multiply the electric field into area. If the field strength is different at different points, we'll take one more example. Just see once. Let's take the next examples.